Welcome. Thanks for joining our presentations. Alex talked about the current state of AI and some of our important survey results in that regard. And what I'm going to talk about here is the current state in relation to where people want to take AI over time toward the goal of artificial general intelligence that would pass the Turing test. And some people think, experts think that we will get there, and some people think we won't get there, but it's still important to have as a goal, as something to aim for in moving AI forward. Our survey of noted AI experts worldwide, on average, they said it would take 87 years to get to artificial general intelligence, with an outlier at 150 years. But again, it's most important as a goal, whether we get there or we don't get there. So here's the status today. Right now we're in an early period of AI, but still a very, very useful one, but far from artificial general intelligence. Right now, what we're looking at is AI where there's lots and lots of training, so lots of observations in order to do relatively simple things, mostly having to do with vision and sound, and few choices to be made after all these observations. Again, really simple things, one-trick dogs, where, for example, there's not a whole lot of context to recognize, for example, that brown irises and green irises and blue irises are all part of something called eye color. So sort of separate training for each of those things. And training and inferencing at a relatively early state for many, but not all of the use cases, not nearly enough usable data, but still very, very good things and useful things happening with it. Where we need to get to is still lots of observations, but for much more complicated tasks where there are many choices to be made, not just, say, for automated driving, forward, reverse, left, right, fast, slow, but lots more subtle choices and more versatile capabilities for the AI devices, and in particular, more intelligence kind of inserted into, in particular, the inferencing side of things, in order to do things like look at human motivation, have more mature human driving, and to do more complicated things in healthcare. So just a few words about AI, maybe a refresher for all of us, is that it ultimately is about machines that can guess much faster than people can. And guessing is kind of inferencing. It is kind of filling in the blanks with incomplete information, and filling those gaps in. And there are issues today around ethics, around legal liability, around explainability, bias in some of the data, but it's pretty clear at this point that the momentum of AI is so strong that those things are not going to stop it, but they do have to be addressed. And our studies show, as I think Alice may have mentioned, that almost all HPC sites are involved to some extent in AI today. Okay, so where does HPC fit into AI? In a very important way, AI is nearly indispensable at the forefront of AI research and development. So it's important for showing where the mainstream AI market is headed in the future. And it also adds to the TAM of the HPC market, that AI capability. HPC acting at the forefront is influencing already the mainstream AI market in algorithms, parallelization, heterogeneous processing, very fast data movement, and especially, I think, the memory subsystems that can fit big problems into it. We're in a hype cycle, but that goes up and down. And HPC and AI together are moving into enterprise data centers to support business operations where they are not the center, the star attraction necessarily, but have to be integrated into the existing enterprise infrastructure there. So where are we in relation to where this needs to go to move forward with AI? First, training data today, as I mentioned, in a lot of areas, healthcare in particular, the useful data isn't enough. It's been described to us sometimes as minuscule compared to what people need, and there's some biases attached, and so people often have to practice dimensionality reduction, which really just means sacrificing some of the fidelity, the realism in it. Explainability is a big issue. Some people say that, this is the year of explainable AI, and meaning people working on that. The trust issue for deep learning is difficult. It's not explainable. Lots of hidden layers, and some of the experts say, well, it's not getting better. And will deep learning, how far will deep learning take us as a methodology, or will a different and new methodology have to be adopted? But for right now, deep learning is kind of a very, very useful methodology, and inferencing holds out hope because it doesn't have the explainability issues that the training side does. As I said, AI is very task specific. What's happening, people are working, as you see on the right there, on synthetic data, which can help with the bias problem and so forth. People are working on making AI more explainable, in particular boosting inferencing ability. That's kind of inferencing side is kind of the IQ of the system. And so more emphasis is happening on the inferencing side. And as far as the task specific kind of thing, AI right now is mostly focused on, as it were, one sense, either vision or hearing and so forth. But those are being combined now. So a big trend is multimodal AI that combines multiple senses. Haptics has been part of AI touch for decades now, work out of places like Ohio State, and that's getting integrated. But perhaps the biggest issue has to do with the two approaches to AI that have been there since the 1950s and 60s. One, the one that's predominant right now, based on trying to kind of mimic the functionality of brain neurons. That's the main methodology now. But the other one looks at more at sort of deeper levels of symbolism and so forth that happen in our brains. And so people are now trying to combine those two things, and especially because the people who argue on behalf of the method, it's not predominant today. So often think that might be 80 or 90% of human intelligence that's being ignored by focusing only on things that can be learned as opposed to the innate intelligence that we possess. Most of you have seen this before. These are the main commercial use cases for AI, and I won't really go into them here, but these are all growing very quickly. And the other part that's really kind of important for both HPC and AI, and the combination of the two, is edge computing, which, as you know, is just an extension of distributed computing, where most or all of the computing is done at or very close to the data sources, such as the ones listed here. And this is in contrast to the practice that's been of sending big data, at least, to data centers or clouds. The benefits are faster response times to local issues. You want to catch the criminals before they can get away. You want to inform a car what's around the corner, an automated vehicle, before it actually has to go around the corner, and so forth. And there are military and civilian applications to both of these. Other benefits are higher end autonomy, because you don't need to share resources. Higher reliability, in the sense that locally at the edge, you don't have to deal with switches that could fail, and potentially better security, because you're not sending so much data over vulnerable networks. But on the other hand, edge devices today are not generally designed with high security in mind. That needs to change. And a very, very big advantage is scalability, which means that, as the data grows and grows and grows, you can keep adding these relatively low cost edge devices. You don't need to add big supercomputers at the edge and so forth. Well, what is HPC's role finally in edge computing? It really comes into play when you need broader area situation awareness and control. At the edge, you're going to need to have car-to-car communications for automated driving, and you'll have and that needs a very, very quick response time, so it has to happen at the edge. But if you want citywide traffic control, then you need a wider area capability, and you need to look at a lot more data, and that's where high performance computing comes into play. And you see a little depiction there of how that works with the Internet of Things, the edge devices, in other words, and then some computing capability at the edge there. And then the smaller subset of the data, a much smaller subset of the data, which can still be lots and lots of data sent to HPC systems and clouds or on-premises traditional data centers. And then the last element of there, you see that sort of close, the one labeled edge that's close to the Internet of Things. There's this concept of fog computing, which is just, say, a small cluster that is close to the edge and can do more computing than edge devices or near edge devices themselves. But the fog computing devices still have to send things off to HPC systems for kind of much deeper analysis of the situation. So thank you very much.